Okay, this is actually take 2 of Chapter 7, Problems 99 and 101. If you're watching this and it's clear, then be glad that it's take 2, but that's why the answers are already written down. So first of all, Chapter 7, 99 and 101 are really a lot alike. They take the same sets of elements and they ask you to rank them according to size and ionization energy. So the first set, tellurium, sulfur, and selenium, are right on top of each other in the periodic table. Here we have tellurium, selenium, and sulfur. So when it comes to ranking them according to size, the smallest one is sulfur, and then selenium and tellurium. And we're just going from top to bottom, smallest to large. So the elements right above each other are going to be smaller, and they're going to get bigger as they go down the periodic table. Now, ionization energy is going to be just the opposite when they're right on top of each other like that. Tellurium is going to have the lowest ionization energy, and sulfur the highest. And that's because the closer we are to the nucleus, as we are in the sulfur, the harder it is going to be to rip off one of those electrons. The farther away we are from the nucleus, so 2 additional shells down, is going to make it a lot easier to rip an electron off because we get less of that nuclear interaction, that nuclear pull on the electrons. Okay, so the second set of elements that we have are potassium, bromine, and nickel. So let's find those in the periodic table. You're probably looking at a periodic table of your own in front of you. And so we can come up here and we find our potassium right here. And, oh, I should have pre-found these. Oh, and there's our nickel right there, and our bromine. So with the first set of 3, we were looking at elements that were in the same column up and down. Now we're looking at elements in the same row. Now, as we go across the periodic table, we actually get smaller. The bigger nucleus within the same shell pulls harder on those electrons, keeping them a little bit more tightly bound and closer to the nucleus. So bromine, the farthest to the right, is going to have the smallest size, the smallest atomic radii. And potassium, the farthest to the left, is actually going to have the largest size or atomic radii. Okay, ionization energy is going to be just the opposite. Potassium, being in the first column, only has 1 valence electron, and that 1 valence electron is going to come off very easily, compared to bromine, which has 7. It wants 1 electron to look like its closest noble gas, so it doesn't really want to lose one. And so this is going to have the highest ionization energy and be the least likely to ionize or lose an electron. Our last set of 3 are barium, silicon, and fluorine. Okay, so let's come up here and find those. And first we have barium right here. And we have, if we come over here now, we have silicon and fluorine. So now we're going kind of kitty corner up as we go. So if we look first at size, we're basically going to rank these by size, as fluorine is the first for 2 reasons. Primarily because it has the lowest energy level. It's in the energy level N is equal to 2. And it is the farthest to the right. Both things are going to make it smallest. And then silicon being 1 level down and a little farther to the left. And then barium being all the way down near the bottom of the periodic table has the highest energy level and is the nearest to the left, which both things are going to make it the largest element here. Next we have for ionization energy, we're going to rank them as barium first, again for 2 reasons. It's farther down the periodic table, higher energy level, and it is farther to the left, which means it is much easier to take an electron off of barium than it is from silicon. And last, fluorine, because fluorine is in that upper right hand corner, which is one of the least likely, well, the least likely place to lose an electron from.